For our first design project in circuits, we were tasked with building an electromyogram or EMG device, which would measure the electrical signal from a muscle, in our case, the muscle on your bicep in your arm, and it would filter out the signal noise and show you cleanly the electric activity going on in your muscle. So to do this, we need to filter out the signal noise, which are low hertz or low frequency signals below 20 hertz and high frequency signals above 1000 hertz. And we also need to amplify the signal by a gain factor of about 2000 because the voltages that are coming out of our muscles are very small. So if we want to be able to see them on the scope, we need to amplify them by some great amount. The first piece of the circuit that had to be designed for the proof of concept testing was the voltage divider. A voltage divider is a very standard circuit element. It's just a voltage source connected to two resistors in series, and then the output voltage is measured across the second resistor. So in my case, I knew that I was going to be inputting a 1 volt sine wave, and I wanted to get an output of 1 millivolt. So I chose resistor values such that the voltage across the second resistor would be 1 millivolt. So as you can see, I chose a 100 kilo ohm potentiometer and a 100 ohm resistor, and this gave me a output voltage of 1 millivolt. The next thing we want to do to the signal is amplify it, because we are taking a very small signal, and for the proof of concept it'll be the 1 millivolt, and for the actual test it'll be the signal coming out of our arm, and so we want to be able to see it on the scope, so we need to amplify it. For that, I'm choosing to use an instrumentation amplifier, which takes two different input signals, takes the difference of them, and then amplifies it. For the proof of concept testing, the second input will just be ground. For the actual test, the two separate inputs will be from two separate electrodes placed at different points on the arm. So to set the gain of the instrumentation amplifier, I chose two resistors and placed them in parallel across the instrumentation amplifier such that the total gain of the amplifier would be 2000. The next piece of the circuit that I designed was the bandpass filter, and I chose to do a passive bandpass filter, which means that you essentially take a low-pass filter and a high-pass filter and you chain them together. So that's what I did, and that's what you can see in the drawing shown. And I chose capacitor and resistor values such that the cutoff frequency of the low-pass filter would be 1002.2 hertz, and the cutoff frequency of the high-pass filter would be 20.2 hertz, which puts me well within my desired range of 20 to 1000 hertz in the pass band. With all of these pieces designed separately, the only thing that was left to do is to put them together. So here you can see the circuit diagram for my first design. So you'll see first the input signal goes through the voltage divider, then is amplified by the instrumentation amplifier, and then goes through the bandpass filter. As well, on the bottom of the image you can see the transfer function, which is nothing more than a multiplication of the transfer functions for the three individual circuit pieces. Shown here is the boat plot for my first design. The solid black line on the plot represents what an ideal bandpass filter would look like, given the cutoff frequencies that I calculated for my circuit components. And as you can see, at low frequencies, the data is in very good agreement with the theory, suggesting that our high-pass filter is working well. However, at higher frequencies, we see that the signal is being attenuated prematurely, suggesting that there's something wrong with the low-pass filter or that the cutoff frequency may not be high enough. So to rectify this problem, the first step that I took was to increase the cutoff frequency of the low-pass filter. The first thing I did was increase the cutoff frequency of the low-pass filter to 2000 hertz, and I took some more data in the high frequency range and added it into my first data set. And I put them all on the same plot, and I saw that the data points were lying on the same curve. So then I increased it even more to 20,000 hertz and found these data points also fell along the same curve. And then, as another step, I removed the low-pass filter from my circuit entirely, and I took another set of data points, and I found that all of the data points were lying on this same curve. So this led me to believe that there was something going on in my circuit that was acting as a low-pass filter, and it wasn't that my cutoff frequency was set incorrectly, but there was something happening in the circuit that I had not foreseen. Shown here is a gain versus frequency plot for the instrumentation amplifier model that I used in my circuit, the INA 126. And as you can see, the highest gain that is actually specified on this circuit is a gain of 1,000, whereas in my circuit I had a gain of twice that, of 2,000. And as you can see along that 1,000 gain line, the instrumentation amplifier will begin to attenuate high frequencies starting at around 400 hertz. And it was whereas I was seeing that the signals were starting to be attenuated around 200 hertz. So when you consider that my gain was twice the maximum on this chart, it explains the low pass filtering effect that I was seeing from my circuit. So having realized this, then I had to go back to the drawing board and try a different method to filter out the low frequencies and the high frequencies from my EMG signal. My next option was to use an active bandpass filter, and the circuit diagram for that can be shown here. And what an active bandpass filter does is it uses a combination of capacitors, resistors, and op amps to both bandpass a signal and amplify it at the same time. So I chose resistor and capacitor values such that my cutoff frequencies for the bandpass would be in the range of 20 to 1,000 hertz. And from those resistor values, I then calculated a gain factor for my active bandpass filter of 72.15. With the completed design for my active bandpass filter, I was then ready to build my second design. I did have to change the resistor value of the RG resistor in the instrumentation amplifier to change the overall gain factor of that because I no longer needed the gain of 2,000 to come solely from the instrumentation amplifier. So I selected a resistor of around 3.3 kilo ohms, and this gave me a total gain factor for my entire circuit of just over 2,000. Shown here is the Bode plot for my second design. Again, the solid black line represents the theoretical values, so the ideal bandpass filter. As you can see, using the active bandpass fixed the problem I was having with the passive bandpass, in that both the upper and lower frequency ranges are now in good agreement with the theory. With the proof of concept testing complete and successful, it is now time to think about plugging myself into the circuit. But there's another aspect of the problem statement that asks that we connect an LED into the EMG circuit so that when the muscle electronic signal registered, the LED would turn on. So to do this, I'm going to use a comparator, which is an op-amp configuration, which you can see in the figure here. You plug your input signal into the non-inverting input, and then the inverting input, you input a reference voltage. So because I didn't know what the reference voltage needed to be to turn the LED on, I plugged a potentiometer into my circuit, and I connected it to the same 9-volt power supply that was powering the op amp and the instrumentation amp in my circuit, and I plugged the wiper leg into that power source and the other two legs of the potentiometer to ground into the non-inverting input, so that as I swept the potentiometer through its range of resistances, I could find the right ratio from one side of the potentiometer to the other that would ensure that the diode turned on at the correct time, only when the muscle was flexed and generating the electronic signal. The circuit diagram shown here is the actual design I used when testing my EMG device. So you can see that going into the instrumentation amp are the two input signals from the electrodes on my bicep, and the ground was connected to my elbow. And then it just goes through the instrumentation amp, through the active bandpass filter, and then at the output of the active bandpass is where we take the scope input, and then the signal continues on through the comparator to light the LED. Okay, so I'm connected into my circuit that I've built, and basically what I have are these two electrodes that are connected on my arm, and they're going through an instrumentation amplifier, which is taking the difference and amplifying it. And there's also this ground connected over here on my elbow, which is just giving a reference for the whole circuit. And so after it goes through the instrumentation amplifier, it's being filtered through an active bandpass filter, which is throwing out the low frequencies and the high frequencies and amplifying it again. And then you'll see the output here on the scope. And also this diode will light up. The following clip shows my EMG circuit device in action. I would say that overall I'm very happy with how the results of my EMG device turned out. As you can see from the preceding video, the signal-to-noise ratio was very good, in that you can clearly see the muscle's electronic signal on the scope, and it greatly overpowers the noise signal. And also we were able to filter out the appropriate signals to get a clean read from the muscle's electronic signal that it outputs. So overall, I'm very happy with how my circuit turned out.